In this experiment, I'm going to be synthesizing and identifying a carboxylic acid. To synthesize the carboxylic acid, I'm going to use this molecule called maleic anhydride, and I'm going to react the maleic anhydride with solid zinc and a little bit of hydrochloric acid. This is going to give us an unknown carboxylic acid. Once the carboxylic acid has been synthesized, to identify it, I'm going to measure its melting point, and I'm also going to be using a titration to help determine the molecular weight of the carboxylic acid. Let's watch. We're going to be starting with about 2.5 grams of maleic anhydride. .512. And also for this reaction, we are going to be using some granular zinc. I'm going to measure that out at the same time. We need about 1.8 grams of the zinc. Quite a bit more, but that's fine. 2.067. First, I'm going to dissolve the maleic anhydride in water. Maleic anhydride does not dissolve very well in water. It's not very soluble in water. So to help it dissolve, I'm going to be stirring it with a little magnetic stirrer. And then the water, I'll be using 15 milliliters. I'm going to heat it up, and it should all be dissolved at around the time that the water reaches its boiling point and starts to boil. The maleic anhydride is done dissolving, so now I'm just going to move this flask to the front of the hot plate where it's not so hot. And next I'll be adding the zinc. I want to add the zinc in 3 or 4 portions. I don't want to add it all at once, so I'm just going to pour some of it in, and then after each one of the additions of zinc, I will be swirling it around, mixing the solution together. However, the zinc is not going to dissolve at this time. Now that I've added the zinc, I'm ready to add the last ingredient, concentrated hydrochloric acid. I have 5 milliliters of the hydrochloric acid, and I'll be adding it to this flask in small portions. You always want to be careful when you are adding an acid to water, especially a concentrated acid, because it does generate a lot of heat. The hydrochloric acid is going to dissolve most of the zinc, and as more and more hydrochloric acid gets added to the flask, you'll notice that it does start to turn kind of a cloudy light gray color. It is important to note that the heat is not on at this time. Once I've finished adding the hydrochloric acid and it appears as though the zinc is pretty much completely dissolved, I will then turn the heat on and I will allow this solution to boil. That will cause the rest of the zinc to dissolve, and it will also cause the reaction to take place. Next, I'm going to be performing a hot gravity filtration on this mixture. The reaction is complete, the product is dissolved in this hot water, and then there are also some undissolved impurities in the hot water that I want to get rid of before the next step of the process. The product is only soluble in water when the water is really hot, which is why I need to perform this filtration while the solution is still hot. I'm going to be pouring it into this fluted filter paper, and during this filtration process, all of the impurities are going to be caught by the filter paper. The product, which is still dissolved in that really hot water, is going to pass through the funnel, and it will be captured in the Erlenmeyer flask down below. So this is a really effective technique of removing solid impurities from hot solutions. Once it's done filtering, then I'm going to put the Erlenmeyer flask back on the hot plate, and I will heat the solution up to the boiling point. There is a little bit too much water in the solution, and so I need to heat and boil the water to help remove some of the water so that the product of this reaction can precipitate. The solution is now boiling, and again, the goal here is to just evaporate some of the excess water. There's a little bit too much water in here for the solid to be able to precipitate or solidify on its own. Removing the water is going to help to get that product to precipitate. So I'll just be watching this until the solution begins to appear cloudy. That's how I will know that I have evaporated enough water. When the solution appears cloudy, I will pull it off the hot plate and let it cool down to room temperature, and then I will put it in an ice bath and let it finish cooling. During this time, I should get lots of nice crystals, which I will then vacuum filter like normal. So here you can see it's just started to get a little bit cloudy. That means I have evaporated enough water. I'm going to allow this to cool down to room temperature first, and then I'll put it in an ice bath to allow it to finish crystallizing. Now that it's done crystallizing, I will be filtering out the crystals. I'm using acetone to rinse the crystals and also to wet the filter paper. This is mostly solid in the flask. There's not a lot of liquid in there, which makes it kind of difficult to filter. Once these crystals are done being filtered, I am going to set them aside and let them dry overnight for analysis. So here's our carboxylic acid product. It's a nice white powder. I'm gonna get a mass on this. So it just fell out in one big giant chunk. This is 1.691 grams. So for this molecule, because we really don't have any idea what this molecule is, and therefore we don't know what its melting point is, one of the strategies that we would use in this situation is to just kind of take a guess at a starting temperature. So I'm going to take a guess at about 150 degrees as a starting temperature for this melting point. And I'm going to set the machine to increase in temperature really rapidly, way more than what we would normally use. So it's going to increase in temperature 10 degrees a minute, which is really fast. And that's too fast to get a reliable melting point on a molecule. But what I'm going to do with this is use that 10 degrees per minute to get an idea of what temperature it melts at. And then once I get kind of a ballpark of where it's going to melt at, then we'll redo the melting point, being more careful about setting the machine up and increasing the temperature at a slower rate. So right now the machine is just getting itself up to that 150 degrees starting point where I suggested that it started at. And if you were doing this and it was melting right now, which it's not, But if it was, then you would just start over with a lower starting melting point and just kind of repeat the process. So we know when we're doing this initial melting point that it's not going to be accurate. It's not going to be reliable. We're just using this as a way of giving us a better starting point for getting a more accurate melting point. So now the machine is increasing temperature, and like I said, it's increasing at a much faster rate than normal. Normally it would be increasing at a rate of 1 degree a minute, which gives us plenty of time to analyze and watch and make sure we get an accurate approximate melting point. But right now it's just really ramping up. And 10 degrees a minute is as fast as this particular machine goes. Otherwise, I would have it go even faster. We are now at 160. And it's still is not even looking like it's getting ready to melt. Now it's at 170. And we're at 180. It does look like it's starting to get a little bit sticky. So we might be coming close. It's definitely shrinking. This is now at 190. And it's possible, I guess, if, it is possible to get an accurate melting point. So maybe we won't have to redo this. It's at 192. And it's pulling itself up the capillary tube, so it's actually not visible anymore. It's like pulled itself. I've never seen it do that before, but it's pulled itself up out of view. So we're gonna have to redo it, and hopefully it won't pull itself up again. And I'm gonna start it at 190. Got a fresh sample in there. The machine I turned it off for just a second, so it cooled down a tiny bit. I have it set to go up to 190 and then increase at 1 degree a minute after it gets up to 190. It's pulling itself up again. What the heck? That is so bizarre. All right, I'm gonna try again. That's so weird.
Yeah.
Right, there's a third sample. Hopefully this one won't pull up out of view. It looks like it is starting to melt. It is definitely starting to melt. It's at 190. And it is done melting at 190. One of the ways that we're going to identify our unknown carboxylic acid is through a titration. And we're going to use about 0.2 grams of this carboxylic acid for the titration. It's going to be very important that we know the exact mass that we're using for the titration.
So it doesn't matter that I get exactly 0.2 grams. What matters is that we know exactly how much we have. So we're going to use 0.257 grams, and I'm going to transfer that straight into this Erlenmeyer flask. But then what I'm also going to do, just in case we have to do another titration, just in case something goes wrong with this first titration, what I'm going to do is weigh out a second sample of the 0.2 grams. And then if we need to do a second titration, we'll use the second sample. We may not need to do this second titration. So if we have to do a second titration, then the sample for titration number 2 is going to be 0.207 grams. All right, we're ready to titrate the carboxylic acid. I'm going to put a little bit of water in here to dissolve the carboxylic acid. The instructions say to use a specific amount of water, but it really doesn't matter how much water you add. You just want to have enough in there to get the reaction started. It also doesn't matter if it's completely dissolved or not at the beginning of this titration, because it will finish dissolving once we start titrating. And it looks like mine it's mostly dissolved. Pretty much completely dissolved. Phenolphthalein is the best indicator to use for this because it's just an acid-based titration. And so I'm going to add a couple of drops. That pipette just squirted way more than a couple drops in there. So again, we're looking for as light of a pink color as possible in this titration. And I'm going to continue in the titration. I'm going to continue using the water squirt bottle to kind of rinse down as we go to make sure that everything is getting down into the flask. And I'll be doing the titration on this white piece of paper to make it easier to see the pink. We're using sodium hydroxide for the titration. And remember, we've got 2 samples, so if this one gets screwed up, then we'll be able to try a second titration. So right away, I'm just putting quite a bit in and trying to get an idea, since as I'm putting this sodium hydroxide in, I screwed up the first one. So I screwed up. I forgot to take a look at the initial volume reading on the burette before we started the titration, which means it's a good thing that I measured a second sample. We're gonna have to start this over. I'm gonna go get the second sample. Okay, so we're titrating the second sample. Since the first time I forgot to read the initial volume on the burette, we'll start with that. The initial volume on the burette is 0.61 milliliters. Now, let's get sample number 2 ready. I've cleaned out the Erlenmeyer flask. Sample number 2 going into the Erlenmeyer flask. Adding a little bit of water to get it dissolved. It doesn't have to be completely dissolved. Just mostly dissolved. And adding a little bit of phenolphthalein. You don't want to add too much phenolphthalein because too many drops is going to make the color change too bright. And remember, we're not looking for a massive color change, we just want a light pink color change. But if you have a ton of phenolphthalein in there, it's just going to turn dark pink no matter what. There we go. Most of the chunks are dissolved. We have an initial volume reading on the burette, so now we are ready for this titration. It's a good idea to lower the tip of the burette down into the flask to kind of prevent splashing out of the flask. Splashing in the flask is okay because we can rinse it down. And right now I'm titrating kind of quickly because I'm just looking really carefully to see any sort of initial color changes to pink. As soon as I see any sign that this is slowly starting to turn pink, which it is now, Now I'm gonna start being a little bit more careful. And that was barely pink. Like you may have not even been able to see that because it was such a light color pink. I'm gonna rinse down my splashes. Those could be sodium hydroxide splashes. I wanna make sure that they're down in there. And pretty soon you'll probably be able to see that the color when I add sodium hydroxide, it is a little bit pink, but it goes away immediately. Remember that the sodium hydroxide or the phenolphthalein actually reacts with base to form that pink color. So what's happening right now is that as that sodium hydroxide is being added into the flask, it's reacting with the phenolphthalein before it has a chance to react with carboxylic acid. But then, so it turns pink, but then it reacts, the base reacts with carboxylic acid and the pink goes away. So what this means when we see the pink coming and going like this, what this means is that we're getting to a point where there is less carboxylic acid in the flask. We're getting closer and closer to the end point of the titration. Swirling like this during the titration, one of the reasons why we do that is to help with the reaction, mix everything together. But another reason when I'm swirling is to help rinse stuff down the inside of the flask. And also in titration, my technique here, instead of trying to set the burette up to go drop by drop, which takes a lot of time, I just move the stopcock 90 degrees from one closed position to the next closed position, which is a pretty easy motion, and it adds just a really small amount, less than a drop. I'm also keeping a little bit of an eye on the burette because, as you know, if the burette runs out of NaOH, then we would have to start this titration over again, and I don't want to do that. So I'm making sure that it's not getting down too close to the empty spot. The pink color is lasting longer, so it is getting closer and closer to the equivalence point. And the phenolphthalein color change is actually at a pH that is higher than 7, so the indication is actually past the equivalence point. When the color changes, you've actually gone a little bit past the equivalence point, but it's close enough that we get pretty accurate results. So it's definitely really close. That I thought was going to be it. I thought that that one was going to actually have the color change. That looks like it. Look at how beautiful that is. Barely, barely pink. like so barely pink. If I keep swirling this, it is going to absorb carbon dioxide from the atmosphere, which is acidic, which will make the color go back to colorless eventually. But it's pink right now, and it's such a light pink. I like to say your titration should be such a light colored pink that you should ask for a second opinion to make sure it actually is a light pink color. What I'm going to do just to verify that this actually is the equivalence point, so what we're going to do is read the volume on the burette right now. It is 38.2, exactly, 38.20 milliliters. And then what I'm going to do is add a little bit more because I think that I'm at the equivalence point right now. So if I add a little bit more, it should go, you know, definitely pink. Look at that. And I think that that's a color that a lot of people would be pretty happy with, but that's a pretty dark pink. So I'm not going to read the volume on the burette now because the previous volume that I had was the actual endpoint. Adding a little bit more just kind of gave me a confirmation. And then also, like I said, this is actually, I'd be pretty happy if I got this equivalence point, so I'm really happy with that very light pink color.